resource person for the first session. We are honored to have with us Dr. Prabhat Gupta, a distinguished expert in the field of ubiquitous computing. Dr. Prabhat Gupta is currently serving as an associate professor in the Department of Computer Science and Engineering at IIT BHU Varanasi, and also he is a head for Center for Computing and Information Services at IIT BHU. Previously, he had held a significant role as a technical lead at Samsung R&D Bangalore. He earned his MTech and PhD degrees in computer science and engineering from IIT Guwahati and his BE degree in computer engineering from Government Engineering College, Ajmer. His research interests include Internet of Things, ubiquitous computing, wireless sensor networks, and human-computer interaction. Dr. Hari's work has been widely recognized with numerous publications in prestigious international journals and conferences. Moreover, his ability to bridge theoretical knowledge with practical applications makes his insights invaluable to academia and industry. He has been a member for the technical program committee for many international conferences, and also he delivered many lectures on the wireless sensor networks and ubiquitous computing. Thank you, sir, for accepting our invitation. On behalf of AVN IIT, I welcome you to this session. Sir, are you available?
Sorry. Yes, so I think so. My mic is earlier unmuted. Yes,
Yes.
Yes, thank you. Thank you very much, Dr. Shilpa and AVN IIT for inviting me for this one. And this is really a wonderful FTP, which is a good contribution towards the society, towards the academic institute for enrich in this direction. And this is right now a burning topic, and definitely, especially for Indian academic need to do. And this is really thankful for AVN IIT for organizing such type of the event and courses for faculty as well as for the student. So, as Dr. Shilpa already introduced, that I'm Prabhat Gupta from IIT BHU Varanasi, and we are working in this direction. So today I share my slides. Just give me a moment. Yes, so I think so my slides are visible. So here in this talk, I cover the basics of the quantum computing, very basic, because this is the first session of this FTP, as well as this is especially those they are completely new on quantum computing. They are not aware about anything else in the quantum computing. I want to go in a little bit deeper. So the objectives of this session is that we start from the basic, and then we see that the online simulator tools or emulator tools, how we can run the programs on that one. So that means we try to cover the basics in this talk, so that if anyone want to work in a deeper, they have some background, and especially for those they are very first time they're listening the keyword of the quantum computing, how we can start like this one. And so whatever now we will cover, that is one survey paper that is available on archive. So if anyone want to go in the details, they can very definitely they can refer to that one. And if anyone has any point or comment, they always welcome to discuss at the same time or write on the chat box. So quantum computing. So let's we start here. So yeah, Dr. Shilpa, thank you very much. I think so you can switch off your camera. So if
Okay,
because
sir.
this is 90 minutes, it's a too
Yeah,
long.
sure, sir. Thank you, sir.
Yeah. So quantum computing toolkit, and here from nuts and bolts to sake of tools. So we start from the beginning. So this entire session I just divide into quickly into the three subsection. And first we cover the introduction about quantum computing. Then after what nuts and bolts, that means what keywords are required for the quantum computing, what basic knowledge is required in the quantum computing, and finally how to develop a quantum program in a very first level. So we start from the quantum computing. So very first comes in the mind that okay, what is the quantum computing? Quantum word is of course people are listening their physics subject in 11th and 12th, but that means earlier people are not worried about or not heard about the quantum computing. Even starting 2019 onwards, people are start listening the quantum computing is a burning topic. So if we open the quantum computing keyword, it starts or it comes from the quantum keyword. So quantum computing use the principle of quantum mechanics to process the information. So quantum principle is there that is following the quantum computing. So if you are from the physics department, it's very easy to understand the quantum computing. If you are from the material engineering, then it's also a very easy to understand the quantum computing and other things. So if we, that means indirectly we can say we can divide the quantum computing into two completely broad areas. One is in terms of the hardware side, other one is in terms of the software side. In the hardware side, the physics department and the material, especially material department, they are working on how to make the quantum qubits and other thing in a physical fashion. And computer science, electronics department, they are working on quantum machine learning algorithm, strategy, how to allocate the machine, how to reduce the noise level with some statics or with the, if you use something else so that we can reduce the machine learning with the help of machine learning noise, how we can reduce and other things. So there are completely two different domains are there. So based on our expertise, that we need to decide whether we need to go. It is very tough to work on the both the directions. And why quantum computing is too popular and the burning topic at this time? Because they can solve the too complex problem from traditional computers. So those they are from computer science, they are always familiar with NP hard problems, or NP complete problems. That is a quite complex problem, too complex problems. So, but the quantum computing can able to solve that type of problems also. So, say for example, if you assume that this is the encryption time, we have a very long key, and this encrypted key takes huge time for decryption and other things. But since the quantum computing is so fast, so then they can very easily they can solve the problem and they can decrypt this information. So, quantum works in the both the direction, pros and cons. So two complex problems. So encryption is the too complex problem, but it is also risky that you can decrypt that information very quickly. So that means security threats is there if you use the quantum computing in that case. And how they can solve the problem for speed up the specific task. So their phenomena, their physics is different, so that they can definitely speed whatever the processing time is required. They can do all these things. So this quantum news physics letter they published in 2023 August time, they highlight all the features of the quantum computing, that why quantum computing are so popular and how they can solve the problem. This picture is very interesting. That's the very first time when I saw that, I was quite surprised that. So here, that means there are two completely two different terminologies. One is some lamp is there, another one is the light is there. So they are both are useful for the lighting purpose. So, but we can't compare these two things. That means you can merge the 100 200 this type of the light lamps, they can't compare with the one lighting of the electricity. So they are completely different principles. Of course the objectives are the same, we want lighting from the darkness, but the physical and the principles are different. It's the same thing as that we can't say 100 computer must together make a cluster is equals to the quantum computing. No, we can't say that okay 100 computers makes one quantum, or 1000 traditional computers is the one quantum. Both are the different fashion, their principles are different, their working cultures is different. So but the purpose is of course the same, that both want to solve the problem but in a different fashion, and both have their own advantage disadvantage. Classical computer, they also have their own advantages. Quantum computing, they have their own advantage, but we can't say hundreds of the classical computers equals to the one quantum computer in that case. Now, this is the comparison between quantum computing and classical computing. So here we can go in a little bit that means thoroughly, that we can see that the quantum computing works on the qubits. Okay, they use the keyword of the qubit. So, if your very first time you heard that that is the qubit is that is similar to that the this is the bits in the classical computer, that 0 and 1 bit is there. Here use the qubits keyword, which can represent the 0 and 1 at the same time. That's the beauty of the quantum computing. You can see the two state at the same time. But in the classical computing, either you can work on the 0 or 1. So because of that properties, that you 0 and 1 at the same time, that means there are some states are there in between 0 and 1. So In the quantum computing, we can use or we can utilize that state between 0 and 1. So that means the same size of the operations, they can perform less complexity because we have multiple state between 0 and 1. And here in the quantum computing, they can utilize all the state between 0 and 1. But in the classical computing, they work only either 0 or 1. That is the issue. So because of they use the some sort of the binary 0 or 1, that means linear growth is there, 1:1. If you put some more input, then you can find out more output. More effort is required for processing, more outcome is there. And that is the classical computing. But in the quantum computing, that is in between 0 and 1. So 1 qubit, that means between 0 and 1. If 2 qubit, then we have the square of that one. So that is the exponential growth is possible in quantum computing. So your processing power effort is required less and outcome is so high. Here processing power effort is as good as the outcome. So in the classical computing, you have one processor, you have two processor, that means you can find out the 2 times faster computers. But here if you have the 1 qubit and 2 qubit, then the exponential growth is there in the quantum computing. So because of that reason, very first thing, quantum computing is not suitable for simple problems. Those problems, they are very simple problems, a very small size of the problem. Unnecessary we are using the quantum computing. Say for example, if you want some searching of the elements in a very small level of the quantity of the items, then why we are using the quantum computing? So if you see the graph, that initially the graph is more or less same as this one, then after they go to the exponential like this one. So if your problem is more complex, then you need to switch the classical computing to the quantum computing, because the quantum computing is suitable for the complex problems which are not solvable on the classical computing, or they can solve in the quantum computing, classical computing, but the time complexity is very high, and such time complexity is not acceptable in real time scenarios or real case scenarios. So some of the physics principles or some of these nature problems where a huge data set is there, you need to solve the problem in a given time period. Quantum computing is the perfect solution in that case. And of course, you need to pay the cost in terms of the hardware cost, in terms of the noise and errors. So here we can see that the third picture is quite interesting, that all the 0 and 1 qubits are there, but they also have the, along with the 0 1, they have the states. That means they have some angle, and which is use a different keyword. I will show one by one. So if assume that this is the 0 and this is the 1, in the quantum we use the qubits, and qubits has some angles entitlement of this one. So they have some angle with between 0 and 1. But in the classical computing, they have either 0 or 1. So in that case, we miss all these positions, whatever the positions are possible on the quantum and quantum qubits. So because of all these positions, you need to put the more inputs for more output. Here, less inputs are required for higher output. So this is the difference between classical computing and quantum computing. So one thing is clear, uh, quantum computing is suitable for complex problem, large size of problem. Classical computing is suitable for a small size of problem and simple problem. Quantum computing is need to pay a high cost in terms of the hardware, in terms of the maintenance of that state. Otherwise, you lost their properties. Classical computing is required the less cost, or the cost of the maintenance cost is very less in the classical computing. But yes, classical computing has some limitation. They are not able to solve the complex problem. Then only the quantum computing options are there in that case. Now we can see the market, what people are doing, or what these private industries are doing, how much they invest in this quantum computing. You can see the growth of that one. 2019 onwards, we heard the word of the quantum computing. Before that, people are not aware about the quantum computing. They know, of course, the quantum, but not the quantum computing. So market is starting from the 2019. Of course, this strategy is little bit changed right now. The growth is so fast as compare what people are predicting earlier. So you can see that the market capital is 410 in 2013, and 2014 575. So increment is only 165, but right now the strategy increment is very high. So but if we follow this one, whatever the TI source of 2020, if we follow this one, still the market on 24 is the 575. It's a very big number in the quantum computing in that case. And see the next 5 years, 2024 to 2029, within 5 years, the market comes for 500 to 2500. 5 times more. So the quantum is the future, and definitely market is ready to invest in this size of the quantum computing market worldwide. So we need to also do in this direction. This picture is very interesting. This picture need to think that what we are doing, being as India, and what other countries are doing, what is the possibility in the quantum computing. So you can see the investment in the quantum computing that, of course, the source is the 2020 or BS business standards. They give the sources that the quantum computing investment in the China, that is the $10 billion. But the other countries, there's US, Europe, and India is the $1.14 billion only. So think about that. What the investment of the India is compared to the other countries. So of course, initially investment is required. A huge investment is required in the quantum computing, and especially in India, that is the Andani groups and other things. They are doing a huge investment in quantum computing as compared to the other investment. So of course, this is the next, that means the burning keyword after the AI and ML. So we see last 5-10 years, people are focused on AI ML, and most of the investment in AI ML research are in AI ML. But now in this quantum comes into the picture, and of course the few countries are quite exciting in this direction. So US, Europe, and China and India, if four countries are together, then they cover the entire market in that case. And who is the largest player, that means in this market? So one is the IBM, Google, Microsoft, Intel, Alibaba. These are the main players. And why we need to know these main players? Because of they provide the platforms of the quantum computing. As of now, still that means, or even not only today, but after some of the couple of years in the future, we are not able to. That means have the quantum computing or store the quantum computing in the institute level. So definitely our dependency is anyhow in this type of the large firm, IBM, Google, Microsoft, and others. So in that case, we need to know that the name of this company. So this what IBM or Google or Microsoft they do. They design a quantum machines in hardware fashion. They give some credits to use on that one. So as a experimental point of view, as a research point of view, right now we are also using the real quantum machines on that one platform, not at the institute level. And thanks to these, that means large firms, they provide the academic space on all their platform. That means if you are doing some research work on the quantum computing, small size of the example you can easily run on the whatever the machines are there, the real machine of the quantum computing. Those they are provided by these IBM and the Google and Microsoft and other things. And that it is very tough because not only because of the cost, but also other requirement of the quantum computing machines are very high. Say for example, desired temperatures and vibrations and other things, which is very costly and not feasible in the academic organization. So that means anyhow this is the good platform for that one for using, and not only for that one. Now, there is one important thing is that the quantum computing will not replace the current devices. That is very important. So we can't say that traditional computer will replace with the quantum computing. That is, other two different things are there, and their physical phenomena is their requirement is different. So, say for example, data collection and the data pre-processing in the machine learning, you can use your own traditional computer or traditional systems. Computer may be possible high-end computer, say for example, supercomputer. So you can do all the processing powers and all the pre-processing, data preparation, or all other things on your supercomputer or one traditional classical computers. Or once you require the machine learning time or take the decision time, then you can use the quantum machine learning and quantum computing phenomena. So we can't say that whatever the traditional machine can replace with the quantum computing in future. No, right now it is not possible that they have the both different roles. So initially you can use the traditional computer for prepare your problems, and once the problem is ready for the solution, then you can put that problem on the quantum computing. So this is the history. So why we need to know this point? Because of we can't stop the research in the traditional computing direction. So whatever the classical machine learning algorithms or deep learning algorithm, that is still going on the research direction, and quantum machine learning and quantum computing problems are the different directions. So we are not say that okay, we need to stop the research in the classical computing because of the quantum computing is future in that direction. So this is a quite interesting picture. Of course, this is the 2020 right now. Investment is huge in these countries as compared to other countries. Now this is the 2024 R&D. This is the latest picture that we have collected from other sources. So here they highlight that who is the player who is ready to invest or invest. So they invest $10.7 billion in 2024 of all these companies. So you can see that almost all the main players are there. So why they are investing, because they know the future of in this. So if say for example, if you take a very simple example of quantum machine learning, and you go to the make my trip for booking the ticket from source to destination, and if they take the decision takes around 30 seconds or 1 minute, you feel not a good experience. But same the make my trip hired the servers of the quantum machine servers with the help of Microsoft, IBM, HP, and other things, and the searching time is 20 seconds, then definitely people say the better experience. So what they will do, that cloud-based solution, either this is an example of the that means make my trip. So similar to that one, companies in place of traditional server, if they put their problem on the quantum servers and they can solve their problem in a fraction of the second, then definitely user experience is the rich and future is that is the winner of that company. So that's where these whatever the clients are there, they definitely want to switch from traditional server to the quantum servers, and that's where these all the players they are fighting with each other. So who else will the winner, who else will provide the server as soon as possible in a decent fashion for to the users. But as a research point of view, both directions are open: classical computing and the quantum computing. Now, assume that we are familiar with the quantum computing platform. We are familiar with the keyword of the quantum computing. So, quantum computing works on the quantum principles, and of course, that is in towards the processing power, towards the computational power in the direction. So, these are the dimension where we can work. So, based on our domain expertise, we need to find out the applications of the quantum computing, and where we can find out the space of the quantum computing for future work. So you can see the cybersecurity is the hot topic, and some of the articles I've gone through that they are claiming that if quantum computing comes in a perfect fashion, then nothing is secure, because they can decrypt any key or they can crack any key within a fraction of that time. Very soon they check all the combination, whatever the combinations are possible, and which one combination is the perfect they can use, and they can crack this one. So quantum computing, if the quantum computing work perfectly, then cybersecurity has the both the direction. That means you can that means secure your system, and you can also unsecure your system, because you can very easily to check the all the combination, whatever the combinations are there, and definitely there is one combinations work perfectly. So cyber security, that means that means whatever those people they are working on the cyber security, they are closely monitor the performance or the progress of the quantum computing. So anyhow, in the future, they need to keep in the mind that okay, the quantum computing is also there, so they need to secure the system based on their demand and based on their applications. The another direction of the quantum computing is the drug development. So this is also a very hot topic, burning topic. So because of DNA architecture or DNA structure is quite complex, and the data set is very complex and required huge processing in that case. And this processing is not possible in a given time period. So if we use the quantum computing, then definitely we can solve the problem very easily in that case at the same fashion. And what's happened that if you are not solving the problem in a given time period, then maybe possible they change their states and other thing. So, what were the drugs development or medical science and other things? The quantum computing is really a good achievement in their direction. They are very happy right now. At least their unsolvable problem can solve in a given time period. Of course, artificial intelligence is somehow the part of the quantum machine learning. So once the quantum computing comes into the picture, then various application of AI ML comes into the picture. And material science is fully energetic, and almost all these institute of the material science they are that means comes on the same board of the quantum computing. So IIT BHU also have a strong material engineering department, and various faculty members are working to design the material to solve the material properties or make the properties change the property which are suitable for the quantum computing. So the material engineers or those they are working on in this direction, they got a huge job in the quantum computing right now. Finance direction is if you have the fast machine, you have all together, then definitely you can solve a large number of problems. So a very interesting example is the stock market. So because since the stock market a huge data set is there, you need to predict within a given time period. So definitely finance very easily can solve the problem with the quantum computing with the help of the algorithms. Other green color are the advantage if you use the quantum computing. है ना? So battery management and other things, weather forecasting, traffic, solar and cleanness, all these are the properties. If you use the quantum computing, you have all these advantages. So if you found out a good result, if you find out a quickly result, then definitely that is suitable for the climate, that is suitable for the battery, suitable for the all the decision. Traffic monitoring and other things, if you take the correct time and the correct decision with the help of quantum computing, definitely we can improve the traffic problems, or we can solve the traffic problem easily. And of course, if your problem, you can solve the problem which are the not solvable or the complex problems, then definitely the climate effect and other things are also positive in that direction. So overall, the picture is very clear, and in both the direction, as a research direction is huge advantage if we use the quantum computing, as well as the nature direction, climate direction, CO2 emissions and other things, that is also positive in the quantum computing. So everything is positive. Only the problem is that right now the architecture is very complex, and the requirement of the quantum computing is very high, which you need to pay a huge cost in that case. So people are not still not ready or not aware about that thing. So earlier the plan is that when this is all these are the industrial plan that or the market survey, but IBM also released the roadmap. Of course, these are the company, they are that means they have done the planning of the next 10 years. So this is the IBM, that means what they are feeling, that in which direction they are moving and what is their next plan. So of course, we need to observe closely that what they are doing, and based on that one we can also divert our research or do the research in the direction. So IBM actually start disclose their plan. Of course, before that, maybe possible they are doing or not, we don't know, but they disclose their plan on 2019 onwards, and they have the roadmap up to 2026. So this picture is very complex, and if we focus on that, okay, what they are mainly doing that. So qubits. So we already seen that the qubit is in the classical computing is the bits 0 and 1. Here qubit is the one state is there in between the 0 and 1. So making the qubit, stability of the qubit and survival of the qubit is a very challenging problem in the quantum, and that is main work of the quantum computing. So 2019, IBM proposed a one hardware. See, that is their hardware, not theoretical or not on without paper, or not on the paper. That is really the design or the modulator system of 27 qubit, which is a very big achievement. That first time someone designed a 27 qubit machine. Then suddenly the next year they propose a 65 qubit machine. Then after they increase the qubits. So their objective is that increase the size of the qubits. Once you have the more qubit, you can parallelly process or you can solve the problem as quickly as possible. If you have less qubits, then you are not able to solve the problem quickly. So the objective is that how we can increase the qubit. If you have 27 qubits, then definitely you can solve the problem up to a certain levels, not scale of the problems. If you have the 65 qubits at the same time, definitely you can parallelly inject all the problems, entire problem on the machine, and the machine can solve all these things. Otherwise, you need to break the problem into the sub problems, or sequentially you can enter the problem inside the machine. So IBM Quantum, they are working in this direction. And of course, right now, 1,300 plus qubit machine is there. They are claiming in this, and they are assuming that up to 10,000, 2026, they assume that 10,000 qubits. That it's an imaginary number, but yes, they are claiming that they will reach this number at this level. And if someone reach the 10,000 qubits, I don't think so that then any problem will left on this universe. So this is their claim that they can achieve the 10,000 to 1 lakh qubits at the same time. But as of now, whatever the machines are available for use for our use purpose, or and the IBM platform is 27 or 65 qubits, like this type of machines are available, which has the limited. And after certain qubits, why? Because I'm saying that this is a very imaginary number. After certain of the qubits, when you assume that someone has the query. Okay, I will see that in the queries. So that is up to certain level that qubits increment is possible. But after that, once you increase the qubit on a one same chip or same machine, then noise is very high. And noise, that means compromise with the quantum states. Stability of the quantum state of making or sustainability of the quantum state is a very challenging problem. If you increase the temperature, if you decrease the temperature, anything changes is there, then this qubit, they lost their properties and there is no state is there. They lost their properties. So their property is maintained up to a certain constant is only the possible. So when you increase the qubits, in the machine, then it is very tough to survive that machine or maintain that machines. Okay. That means on a same chip. Of course, when we break the chip into sub-chips, then it is possible. But if you assume that I can make a complex qubit chipset, then there is some threshold is there. After that, a huge noise is there, and because of the noise, that means there is no meaning of it all in that case. So you can see that of 27 qubits, they have one chipset is there. One, in other words, we can say, if we are doing in a non-technical word, we can say one processor is there. So 27 qubits we can put in a one processor, 65, 127, 433 qubits on a one processor we can put, and 1 to 1 qubits we can put in a one processor. But after at this level, they assume that the noise is very high, maintenance of the state is very complex, and also that is not required that qubit at the same time. So what additional architecture or alternate is that they divide this one on 133 qubit multiplied by p chipsets. So think about that. They changed the plan on 2023. Up to 2023, they uh, focus on this one. Okay, we can make the denser and put all these things together. But at the end, they realize that no, it is not possible because of the noise, because of the temperature, and numbers of other challenges are there. So what they have done, they divide this chipset into the parallel of the multiple chipsets. You know, parallelly, they are working in the both the direction. Make a complex, make a simple, but in a parallel fashion. So here they divide the 1 into the 133 qubits of the multiple small size of the chips, and they interconnect with each other. So these chipsets are connected with each other, and this is the quantum communication. Okay, not a traditional communication. So don't think so that okay there is any delay is there, because quantum is working only for the delay purpose. You need to remove the delay. So if we have the delay of the communication delay and other thing, then it is not possible. So this is theoretically it is zero delay because of the quantum, but practically, of course, some delay is there. No one, you need to pay the cost from this place to that one place. Either you can use the quantum or you can use the classical communication in between to this one. So their earlier objectives were that they want to make a bigger size of the chip, denser chip, not the bigger size, denser chip. But here they start dividing the chipset into the sub chipset in a light fashion or 130. Once 133 is there, then there is no noise, nothing is there. The problem goes sort out. Same as when they switch from 1 to 2 1, so 1386, they face the same problem and they change their roadmap and other things. So they start the uh, intelligent integrity of the subset of the chips. So now they start like this one type of architecture. Then 10K or 100K, even more than that one is possible, because you divide the chipset into like this one type of the architecture. But here they have the one processor. Initially they start from this one, make up to a denser circuit, and then and why this problem comes into the picture? One is, of course, the noise. Because of the noise, accuracy goes down. So in the classical computer, we use the keyword of the loss function. Here we use the keyword of the noise in that case. So when the noise is up to a certain threshold, then okay. But when they go beyond that one, then definitely we need to use a small size of the quantum processors. And these processors has the lesser noise as compared to a bigger size of the processor. So here we can see that after this 2023, when they start dividing of this one or architecture of this one, they focus on the improve the accuracy. Till that, they are not worried about that thing. They assume that their circuit is a one circuit and they are not worried about the accuracy and any other thing, because they know that we have the 100% accuracy. Doesn't matter, don't worry about that. But after that, they worried about the accuracy, and because of that worried about the accuracy, they start in this fashion. And only 2023 onwards, IBM Quantum, they start the quantum software application where, sorry, where they start the machine learning, natural sciences and optimization after 2023 onwards. So before that, they mainly focus on quantum algorithm and application models in that case. And all these green colors indicate the achievement of the, when they achieve all these things, that means this is the real market exists, and this I can indicate that are the futuristic plan, because the slides are 2023-24 images there. And now this intelligence integration and circuit libraries and other things comes into the picture. So this is the model development. They start developing the models. Up to 2022, they have no models. All the algorithms are there. So you need to work on the core algorithm of the quantum computing if you want to work. Of course, this is the black box at that time, but models is the easy way. You can do the contribution in that case. You are not required to directly work in this. And models call the algorithms, that means the libraries. So you can directly call the libraries. Here there is no libraries, nothing is there. You can directly work on it. So after 23, they make simple for the end user. That means if you are the developer, you want to design or develop or want to work on the quantum, then models development comes into the picture. They call the libraries, and the libraries call the kernels. So you can see that the kernels also start in a very fascinating fashion. So Qiskit is one platform of the quantum library. So Qiskit is the library. They use the kernels in a different fashion, and this is the system level that what they are doing and where they are doing. So this is the roadmap of quantum, IBM quantum roadmap. Once we, that means that we have the quantum, we familiar with the roadmap, what they are doing, then we need to figure out the technology dimensions of what people are doing and how we can find the space for the research and as well as for the engineer point of view. So of course, one is always there, the quantum computing, where quantum machine learning comes into the picture, all these things come into the picture. So why the quantum computer is the ultra fast is there? You can't predict it, the fastness of that as compared to classical computers. And object is that to increase the qubits again and again and again in this. So some of the, though they are the computer science background, they are mainly working in the quantum computing. But those they are from electronics or electrical background, they are working on the quantum communication. So ISRO is the first agency in India. They successfully use the quantum communication between two buildings. So if you write the quantum communication ISRO, you can find out that article very easily. So in that article or in the practically, they select two buildings. One, of course, both are the ISRO. So they in between two buildings, they successfully done the quantum communication on that building. China is the winner in this direction, and they claim in their papers or in the media or the news, they use the quantum communication up to kilometers. Of course, with the help of relay, not directly end to end the distance the kilometer, but yes, they make the quantum communication network up to certain kilometers. So ISRO in India, they have successfully quantum communication between two buildings. Third one is the quantum sensor. So those they are working on the physical device designing from that is the sensor node designing or hardware side designing. So quantum device designing is also a one level of that one, but it is very tough for us to do work in this direction directly because of the resources, because of that means still that is the black box sort of things. Not of course the simulator tools are there in that time. Fourth, in the interesting direction, almost all the materials engineering departments of all these institutes are fully actually working on the making the material, making quantum bits more and more. And they also designed 2-bit, 4-bit, 6 qubits machine in that labs, other things. So this is quantum material. So overall picture says that as an engineering point of view and all the institute point of view, every direction is open for quantum computers. So that means we can't say that okay this. So earlier, that for the example, the machine learning or the deep learning, the quantum material engineering department, they have no job in the direction. Very few jobs are there, but right now they also have a huge job in that direction. So after familiar with the quantum computing keyword, we focus on that. Okay, the basics of the quantum computing. People are using the keywords of the quantum computing. So there are two very common phenomena or the principles of the quantum physics. One is the superposition and other one is the interference in that case. So superposition, say for example, this is the 0 and 1 bit is there. Superposition says that in between the 0 and 1. So classical computing says that I am 0, I am 1. This is the bit. But quantum physics says that one is the superposition is also there in between the 0 and 1. Practically, that means that, of course, that means it's very tough to think about that. But yes, that state is there, which state is known as the qubit state. So if you have the coin of 1 rupees and that you can toss this coin, there is one head is there, other one is the tail is there. If you flip this coin in the air, there is rotation in the air, that is the superposition of that one. That is neither head or not tail. They are rotating in the air. So that type of states are known as the superposition. And once this coin is, you can catch the coin, then either that is the head or tail. Then once again, they lose their properties and once again they comes in the classical computers. So whatever the intermediate states are there between head and tail when they are rotating in the air, so that time we can say this is the superpositions in between 0 and 1. So they have some angle between head and the tail in that case. And interface is the different phenomena, that is the merging of the two waveforms and making the third one. So this is the interface. So in a constructive way, that they have the same phenomena, that means if two qubits are working on the same phenomena, then they increase the strength of the system. Okay? If they are working in the same direction, but if they are working in the opposite direction, they lose the strength of the system. So this is the interference. So wave function in the two particles and superimpose in or out of the phase. So they destroy their properties. That means because they cut to each other. So there are two main principles in the quantum computing, or differentiate between the classical computing and quantum computing in that case. Quantum physics or quantum mechanics, they also use some more keywords. One is the entanglement. That means quantum state of each particle cannot be independent with each other. So say for example, we already know that, okay, this is the mixing of the 0 and 1. Okay. So assume that this is the classical, you make a qubit in between the 0 and 1. So anyhow, you are not able to distinguish between 0 and 1 now, because they have some state. And now they have some state. Of course, they move from one state to another state. It is possible, but you can't lose their property until unless they have the qubit properties, quantum properties. Once they lose the quantum property, then you can come in the once again bit 0 and 1. But here they have some properties. And another word, a very interesting word, is the measurement. How to measure these things. So whenever you try to measure, whenever you try to find out the state, you lose the quantum states. That is practically, if you stop the process, if you want to measure or try to measurement, in that case, you lose the property. It reverse, it says that you can't measure the state of the quantum machines. So once again, we take our own example that, okay, if you have one coin, one is the head, other one is the tail. If you flip this coin in the air, they rotate or rotate again and again. That is the this one state, entanglement, either 0, 1, or in between that one. And when you stop that coin rotation and you see on your hand that is either head or tail, that means you comes in the classical bit, because you try to measurement, because you try to see that whether this is the head or tail. So whenever you try to, that means measure, or when you try to observe, then you lost the quantum state, and then the quantum machine comes into the classical. And this is the main challenge right now. So say for example, you have the traditional machine learning algorithm. You can use traditional machine learning algorithm, convert into the quantum state, and once again convert into the classical, because anyhow the result is the classical. Face recognize, whatever you are using the machine learning, that is the classical. So anyhow you need to measure, and after measuring you can come in this case. And you are not able to measure, so how we can make the clone? So clone means the copy of the state. You are not able to measure the state, then it is anyhow it is not possible to copy of that state. So you are not able to store or recreate the same state, whatever the state is there. So in the traditional machine learning algorithms, we have some neurons are there, you can do some calculation, some weights are there on the link, and that type of mechanism is there. But here we are not able to see the same weight once again, because the states are changed. Then you are not able to save the state, you are not able to store the state, you are not able to recreate the same state. So in the quantum, if you try to once again the same type of architecture, definitely you are not able to make the same type of architecture. So whenever the classical architecture, CNN architecture is there, you design a quantum machine learning, quantum CNN architecture one time. Another time when you design the quantum CNN architecture, that is the different, because you are not able to recreate the same architecture or same state in between these two. So as we already familiar with the quantum qubits or qubit, and this is the same as the counterpart of the bits in the classical computers. So classical computer has the 0 or 1, but here they have some state. They also have some angle in that, or the superpositions in between 0 and 1. So assume that this is a plane where the 0 is there, 1 is there, and your element or whatever your particle is there, they have at that state in between 0 and 1. So how we can represent in the quantum? We use like this type of the symbols, and alpha and beta are the complex number, and H is the Hilbert state, that is not measurementable state. You are not able to measure this state, and that is in between the 0 and 1 with some complex number in that case, and you flip the coin and you definitely in between somewhere. So psi has some angle in between the 0 and 1 in that case. So this is the representation of the qubits, and of course this is the same as the bits in the classical computing, but you also have some superposition and super angles are there. Now, how this quantum algorithms or quantum algebra works in that case? So quantum algebra works on the gates. So this gate is also the, if for simplicity, we can say this gate is also the same as the logical gate in computer architecture or digital architecture in that case. So they perform some operations, because anyhow we need to perform the operations. We make one primary entity is this one. This is the very first equation in the quantum computing. Whenever you open the book, you can find out very first. Now the objective is that we need to do some operations. We want to multiply, we want to change the state, we want to do something. So how we can do? So with the help of gates, we can do that things. So gate is defined as a unary operation on the qubits. Okay, you need to perform some operations on the qubits. So without operation, how we can do addition, multiplication, whatever you want, you need to perform some operation. With the help of on the gate is possible, and manipulations between the bits and other things are possible with the help of the gate. One thing is here, luckily we find out one positive point is that these are the reversible in nature. That is the first thing we see, that okay, at least we can reversible something so that we can regenerate the same thing once again, whatever we have done earlier. So now based on the algebra, we have different types of the gates in quantum machine. So very basic gate is the X gate, and this is the bit flip gate. So whatever the properties of the 0 state you want to transfer to the 1, and whatever the 1 state you want to transfer to the 0. That means you want to flip the values in between the zeros and 1. So here the algebra says that okay, you can multiply with this vector with that one, and you can flip the values. So if you want, whenever you want to perform the operation of the flipping of the values, you can use the X gate. So in the quantum we say the apply the X gate in place of flip the values like this one. And Z gate says that you change the phases. So this is the negative. In earlier, that is the positive phase by default. That is the positive phase. Now, if we use the Z gate, that is the negative. Uh, that means the phase in that case. So negative. That means this is the 0. The positive one is this one. If we want to talk the negative, that means we are talking about the reverse direction of that one. So whenever you want a negative phase of this one, you can apply for the Z gate in that case. So all these are the gates. They change the that means the value. They use the algebras and other thing. So this is the pictorial diagram presentation of this one. So if assume that this is the X positive, then of course the reverse direction is X negative, Z positive, Z negative, and Y is in this direction. So if we perform the flipping of this one, alpha goes with 1, beta goes with 0. Earlier the beta is with 1, alpha is with 0. So what impact is here? So we can say that okay, this is somehow the reflection of that one. That is, this is at this angle, now that is at this angle. So just flip this one like this. So not change the sign of that one, because this is the X gate. You just flip the value. So just flip this paper and we find out top is the bottom right now, or bottom is the top in that case. Since the gates are reversible, so once again you perform the same operation, you can find out the alpha 0 beta. So that is, at least we can do the undo of whatever we have done. So we can apply two types of that gate. So if you apply the two types of gate, your original value comes in the picture. And as we have already seen that the Z gate change the phase of the input. So still that is the alpha is with 0, beta is 1, original values. But here we want to change the phase of the beta. So what we will do, we can multiply this one, and so now the positive to the negative. So this goes to positive to the negatives. So whenever we use the deep learning, machine learning, and other quantum machine learnings and other things, at that time we need to use this type of the algebraic operations, and multiple gates are there. We will see later on. And H gate is the very useful, and it's used in always in the bigger size of the program as per my experience. So H gate, they multiply the values in a symmetric fashion. So they rotate in a symmetric way. And only the change the values in a symmetric fashion, not only in a one. So earlier this is this value is this one. Now the value shift on this one. So everything flips accordingly. Not only the 0 or the 1 like this one. If you summarize all these gates, so these are the default gates in this one. So whenever you use the real quantum machine or the simulator, you need to select a proper gate for your operations. So starting at the beginning, you need to know about each and every gate. Then you can very easily to apply the gate, okay, which gate is suitable for what purpose. So if we summarize the gates or divide the gates, then we can find out there are the three categories. One is only the unary or binary gates. They have only one input or the binary. This is the single qubit gate. They perform only the single qubits operations in that case. And 2 qubit, they have the 2 qubits input at the same time. That means the 4x4 gates are there. So this is the classification or the categories of the gates, but usually we find out these gates. So all these libraries are there. You can very easily find out the gates of this one. Once we familiar with the qubits and once we familiar with the gates, these are the nut and bolts. Then we make the circuits in that case. Similar as in the machine learning or the deep learning, you have the network is there. And here we have the quantum circuits are there in place of the type network to make circuits in case in one. These are the and at the same time you inject 0, 1, 2, 3 qubits. That means the machine has the 4 qubits at the same time. So if you want to put in an algorithm or in a real machine, so in that case you need a 4 qubit machine. 2 qubit machine is not possible. At the same time you have the 4 qubits you want to inject, you want to do the perform the operations in that case. Here this now this is your input. So quantum name or initial state is, and you move from one state to another state, perform some operations. So here this is the edge gate that we already seen. This is the gate. So these are the gates. They perform the operations in between, and once they perform the operation, generate the result and forward the result to the next state. This is the same as that in the classical machine learning, that you perform some operations and on the neurons on the link and forward that one like this. But here we use the gates in that case. So for the beginning purpose, we are definitely we need to familiar with the gates and other things. Of course, this is a very pictorial diagram. We can understand, okay, this is the input. I will perform some operations and move in the second state, then perform some more operation, move in the third state like this one. But how we can do the programming of all these things on real machine or on the simulator platform? So these are the way to do the programming. So say for example, initially you have the 4 qubits as a input. Initial state is there. So you need to define the initial state. So luckily you have the 0000 initial state. You can write like this one. So this is the way that how we can that means do the programming of the quantum machine. So these are the qubits 0, 1, 2, 3, and these are the initial state. Now the step one. Step one means this one state. So here we perform the X gate with the qubit of 1, H gate with the qubit of 2, X gate with the qubit of 3. So you perform the 3 operations here, operation number 1, operation number 2, operation number 3. Therefore, you are required, the 3 gates are required. So X gate and H gate is there. So X gate with Q1, H gate is with Q2, and once again X gate with the Q3. Now they automatically change the state and save the values of after this X gate, whatever the state, they forward this state to the next state for the next operation performing. So here in the second state, only one gate is there, H gate. So if I want to write a program of this quantum circuit diagram, so I need to write like this one. So initially you need to initialize the state of the qubits. Initially all are the zeros at this state. There is no beta, no one is there. Then beta equals to 0 in that case, and alpha equals to 1. And then you want to perform the 3 operations. You can perform the operation like this one. Then in the second state, you want to perform one more operation. You can perform the operation like this one. So this is the way that the performance are going on and do the operations and other things. Now, of course, this is not a complete architecture and not a that means that is the correct architecture. But yes, as a abstract or the rough architecture, we can say yes, this is working in that fashion. So you can see that the quantum chipset is there. That means the processor, quantum processor is here. After, and, outside of that one, your classical computing, your normal computing, whatever you are using right now. So suppose that you have some data set, some software or some data is there. You use your camera or capture the images like this one. You have the sensor, you have the audio data, whatever data set is there, you have the data. Put the data on the classical computers. Okay. So here the classical computer do the 2 tasks. One is that they do the data pre-processing, data mining, whatever is required, they will do at that level. so that they can prepare the data for the next state. And the duty of the classical computer is that they can convert the classical program into the quantum program, not the operations and other things. So here they will do all these things at this layer. So say for example, classical, first we have the data, we convert the data into classical and convert that one in this shape like this one. So all these are the classical computer. Then they use the electrical wires and other things, they transfer the information in this, and whatever the gates you propose in this one, they do the gate operations at this level. So here what we will do, we can inject the 0000 and 3 gates are there, we inject the 0000 and 3 gates are there, they perform the gate operation. Once they perform the operation, they have the measurement information, and we already seen that whenever you use the measurement, you lose the property of the quantum computer. Now they comes once again the classical and do the classical operation, whatever the classical operation, and generate the result. So if you are the machine learning researcher, you are right now working here. Now you need to shift at this level, but anyhow the data preprocessing, machine data mining is required at this level. And most of the right now the solutions are the hybrid solution. At one level they use the machine learning at this level, and another level is this one. And once again they perform this operation, they comes in this one. Why they are using the hybrid manner, that means classical and the quantum together? Now one thing is that whatever the classical that means neurons, classical cells are there to convert into the quantum is quite complex, and it's a very lengthy process. Another reason is that the quantum hardware in terms of qubits and other things are the limited. So if we try to inject a bigger size of the architecture, and the machine support is not there. So you have that 4 qubit machine, 8 qubit machine, 12 qubit machine. It indicates that you can inject that 4 qubits at the same time. But if your classical has the numbers of neurons are there, how we can inject in that? So what we will do, we need to divide the architecture into the sub architecture. And who else will do? And the classical computer will do. So very big architecture, divide into sub architecture and inject that one, so that they can perform the operation and give the result in the time fashion. So this is the way that how we can quantum computer architecture works in that case. Now we divide the quantum computer into the layers. Basic practically there is no layer. This is a very bigger size of the system is there, but for understanding purpose or for making architecture is more robust, or for catching the bugs or do the contribution, that researchers divide the complete architecture into the 5 layers. So layers makes easy way to understand or find out where is the problem or what contribution, where contributions are possible. So physical layer, of course, the name suggests the physical properties are there. That means hardware related is there. Then virtualization come error. Then after, if any error is there, then after, if you want to implement any logic, and here your application is there. So we will see these layers one by one. So physical layer is responsible for your hardware part. Okay. Actual qubits. So those, they are material engineers or material department faculty members. They are working in this layer. Their main objective is that to make the hardware effectively, make the hardware more suitable for the quantum computing and other things. So this is the physical layer work. Above that, the physical layer virtualization comes into the picture. That that information representation, that how we can represent the information which is correctly, and that means find the goal of the quantum states. So change the one form into the another form. So indirectly, if we say that for understanding purpose, the physical classical computer, the physical is your, that means you can say the network port, and here you change the signals into the binary values, because whenever you connect your network port RJ45 cables and other thing, the signals comes into the picture, and then you need to convert into the binary like this. So virtualization, they create a one change the visualization aspect of that one, that the representation need to change in that case. And here the virtual gates are there to change their that means that representation, not to change the values and other things. So this is a very, this step is, the virtualization very complex. Huge papers are coming right now and that layers. And error correctness comes into the picture, because you change from one phase to the another, the errors are there. Our quantum is still suffer the errors, and most of these people are working for how to control the errors. So error correctness layer implement the error correctness mechanism to create a noise-free logical qubits. Noise-free is anyhow not possible. Definitely there is a noise, but try to reduce the noise in that case. Then comes to the logic work. Of course, you need to make some logics. Otherwise, without logic, what problem we are solving? So once your hardware is ready, once your virtualization is there, representation is there, then after remove the noise, then make some logics. Logic means connection. What outcome is we are expecting? Another thing, how to connect these gates with each other. Then your application comes picture or user interference comes into the picture. So, for example, you see the name as per the image, you image face recognize problem is there. You can enter the face recognize image, and here you can see the name of the person. This is that person. So this is the way that that means how we can divide the solutions or how we can divide the problem in that case. Now we come that what industries are working in this way. So that means there are two dimensions are going on. One is focus on universal gate based quantum computers. They say that okay, we design the gates, connect the gate with each other, and make the quantum computers like this type of solution. So almost all the companies, whatever the main players are there, they are working in this direction. They assume that we have one gate library is there, and we use that gate library for making the quantum computer. So this is the one way that people are designing the quantum computing, and they are get. But here the gate are the reversible and other things, and state is changed from one state to another state. So this is the gate base. Another direction, or some of the companies, they are working a wonderful way. They are working on operations based, a unique computing type of the operation with the object to solve the large scale complex problems. So this is the another direction that these companies are working. So quantum attorney is there, and this is the gateway. So we need to decide in which direction we want to work. So this is an easy way that to find out the work and solve the problem in that case. Picture is very interesting, especially for computer science researchers. They are familiar with P, NP complete, NP hard problems. But in the quantum space, we project like this one. So very broad, or that means topmost super domain is the P space, which is the polynomial space is the class of decision where total space is required, the boundary by the polynomial time in the input size. This is the entire boundary is there. They create a one boundary of solving the problem, but not solve the problem. All the problems are within that boundary. Beyond the boundary space, we don't know about what's going on. But all the problem, whatever the non-problem, whatever the problem we are familiar is within that boundary. In that boundary, there is one NP complete problems are there. All NP problems are there, NP complete problems are there. So here we are not talking about the NP complete problems or P problems. Here we talk about the B qubit boundary error quantum polynomial time problems. This is the class. And exact quantum polynomial time problem, EQB. So this is the domain where quantum algorithms are working. So this is the bounded errors. That means the error is of course there. You are not say that the error is, and can give the correct result with probability of the polynomial time. That means they try to solve the problem with some error, with some probability. And say for example, if the face recognize problem is there, so they match the face with some probability, not 100% they will successfully match the face, another thing. And if we go to the set cover, vertex cover problems, like this type of problems are there. So they have the bounded error. Infinite error is not there. Earlier that all these space are error, we don't know about that. But here we have the bounded error. Error is up to a certain cap, and they solve the problem in the quantum, but have some probability, not exact solution. And here one solution set is the P sort. This is where you need to work, or where you want to work in that case. So these problems can easily solve with the help of quantum machine learning or quantum polynomial time solution. So within the polynomial time, you can find out the solution in 100% successful. So if you want to sorting the element, you can sort 100% successfully within a polynomial time or a quantum polynomial time in that case. So this class is very important. That means whatever the current researchers they are working in, they try to solve this problem. This is how we can move problem from that level to that one level. That is the research direction, how we can move from one to another. Now, once you try to solve a problem using quantum computer or use the quantum computer, that means how we know the performance, whether it is working perfectly or not, or which one is the good quantum machine or which one is not a correct quantum machine. If you have multiple options are there, say for example, if you have the credits, if you have the credits of the IBM and credits of the Microsoft Cisco, then which machine you need to select. So you need to consider these parameters. One is the scale. That means how much qubits they are providing. So one machine they have the 2 qubit, other machine has the 4 qubit. Of course, you need to move the 4 qubits. So of course the cost is high and other things are there. So scalability is the one performance matrix. Which machine is good, which are scalable. Scalability is possible, that you need to focus on that, and what cost you need to pay for that one. Scalability is another thing. And another is the quality of the operations, that okay, what are the operations you are performing, what is their quality means in terms of we can say the noise, or in terms of the operation performance and other things in that case. So these are the parameter that we need to consider. Third one is the speed. Of course the speed is the important part in that case, but usually what's happened is the quantum machine itself is a very fast, and of course speed is also depend on the number of qubits you have. But suppose you have the two machine, both they have the same number of qubits and other things. So in that case, we can say the speed and other thing. And speed also depend on the logic gate supports. So suppose if one machine they are not support that type of the gates, then definitely you need to compromise with the speed. And other, if you make the gate from the with the help of other machine, definitely they take more time in that case. So speed is there, but speed depends on the how much number of qubits are available and what type of the gate support on that qubit. So we can't say that all the type of the gate support on all the machines. No, it is not practically. So they support a certain level of the gates, and whether the gate is suitable for your program or not. If not, then you need to change the program so that they make the suitable. If you take a very simple algebraic operation, so some digital architecture they support the plus in place of multiply. So if you want to multiply 2, multiply by 3. If you have only the plus operation, then 2 plus 2 plus 2. So in that case you need a 3 operation as compared to multiply required only 1 operation. So if some machine they support the multiplication operation, that is much better than if someone machine they support the plus operation. So similar is here, if one machine they are not support that type of the gate, definitely it takes more time. So you need to select the machine they support the gate at that level. Now assume that your machine selection is also done. So you design the algorithm. What type of algorithms are supporting by the quantum machine or quantum solutions? So one is the pure quantum algorithms. That means that is the quantum and design for the quantum or solve on the quantum machines. So they are not worried about other things. So this is entirely a quantum computer that is not use your classical computers algorithms and other things. So here you give the input in a quantum fashion, they solve the problem and generate the result on the quantum and generate the result and transfer this, and then you can change the form from quantum to classical computer. This is the pure quantum algorithms. Another class of the quantum algorithm is the hybrid, that means they mix with the quantum and the classical. So some portion you solve at the classical, some portion you solve at the quantum. So as we already take the example, let's say for example data pre-processing, machine learning, data mining, you can use the classical computing algorithms, and in the quantum you use your whatever the main algorithm is there. So and that is one of that archive paper. They have explained complete details of these algorithms. What is the pure quantum algorithm? What is the hybrid algorithm for quantum algorithms purpose? So if we divide, of course, it's not a direct division. If we try to divide the algorithms, pure quantum algorithm, we find out the 4 classes. One is the quantum algorithm; those they are working on the Fourier transform quantum algorithm. And the objective is that they perform the linear transformation of qubits. So those algorithms, they use the Fourier transformation. They go in a one bucket, and these are the pure quantum algorithms. And the objective is only the linear transformation of the qubit, so that they can reduce the complexity of the system. Second is the class of the amplitude amplifiers algorithms, and why we are required that type of algorithm. They work on the searching with the unstructured data set. That means the data set is not structured. Then you need to go to the amplitude based algorithms. Of course, their complexity is high, but they are suitable for the unstructured data set. So if your data set is unstructured, you need to go in this direction in that case. The third one of the pure quantum algorithm is the quantum walk, and this is very famous quantum. And multiple algorithms are working on this principle quantum walk, and marking elements into the graph. So those they are working on the graph theory or graph coloring problems or graph structure problem. they have the space working in this type of algorithm. So this algorithm base is on the element in the graph. So first they convert the problem into the graph problems, and then after they solve in this direction. And fourth and the last one is the quantum algorithms. They solve the linear equations, or that is matrix inverse problems and others. Then all other remaining problems you can put in a one bucket like this one. So that means whatever the quantum algorithms are there, if we divide, we can find out in the four categories of the quantum algorithm. And based on your application, based on the availability of the resources, you can figure out which one algorithm is better. And hybrid is, of course, the mixing of the algorithms. So, say for example, quantum vector solutions and algorithm based on the quantum machine learning and other things. So, eigenvector or eigenvalues you can use in that case in the hybrid algorithms. So, hybrid algorithms also have their own applications, but the speed of the quantum algorithm is much higher than the hybrid algorithm. But something is not possible on the pure quantum. That's why we need to work to the quantum algorithms. So I assume that all these stories, quantum related or theory is there, but whether it practically is possible, yes, practically is possible. So there are two ways are there. One is the simulator tools on the real hardware. So these are not the simulator tools. These are the same platform on a software fashion. Okay, but of course, your computer is not the quantum computer. So I assume that all the properties are same. You are not feel that okay, you are working on this real quantum machine, or that is one the classical computer and high-end computer and the simulator tools is there. So there are two ways are there. If the quantum computers are not there, hardware quantum computers are not there, then you need to focus on the simulator tools, and you can simulate your own real hardware. So everything is same except whatever the physical challenges are there. Say, for example, may be possible if you perform these operations in that level, some heat generate or some noise is there. That type of phenomena we are not feel experience in that case if you are using the first class. But the positive point is that here hardware restrictions are not there. But if you want to work on the real computer, quantum computers, then machine support the 4 qubit. That means you can perform only up to the 4 qubit problem, not beyond that one. So this is positive and negative. So these IBM and other thing they propose, they have the multiple simulator platforms are there, and you can use any one of that one for your purpose. So that means if we divide, these are the very popular simulator tools are there. State vector simulator. So this is a that means interesting simulator tools for the quantum computing, and they require the less computational but large memory space is required. So this is that means the good if you have the huge RAM memory. Memory means not your secondary memory, means the primary memory. At the same time, you require that level of memory. So this solution is good if you have the supercomputer type machines. Are there a huge memory is there, or the you have the big RAM is there, then you can use the state vector machine solutions. And the second one is the density when a matrix simulator. Here, this is the when noise simulation is required. So you can measure such as the noisy state and other things. Here you are not able to measure the noise because when you work on the practical quantum machine, then definitely noise comes into the picture. So here you need to take care about that. Tensor is the more complex than the state vector machine. So if your problem is the more complex, you can shift here. And of course, here you require the less memory space, but computational complexity is more in that case. So it depends on your availability of the resources. If you have the huge memory and but your processing power is less, you need to go to the SVM, state vector simulator. And if you have the huge processing power but less primary memory, then definitely you need to focus on tensor network simulator in that case. So now we come some companies they provide the platform, similar platform as a simulator, but when you use that, you are not feeling that okay, I'm using the simulator, I'm using the real hardware. You write the program in the same fashion whatever you are using or writing the program. So Google proposed one platform, and this platform may use the Python language. So those they are working on the machine learning, the Python, they can easily shift from their platform to this one platform, and they also handle the noise quantum channels. So if they consider the noise using the Monte Carlo simulation or full density simulators and other things. So that means you can also feel or you can also see the effect of the noise on your tools on your platform if you are using the Google solution in that case. And these two support all standard gates. That is the plus point, a very strong point. That means you can make a simple architecture, you can make a simple network in that case, because they support all type of the gates in that case. So numbers of combination you can check with each other in that case. And there are two three options are there. One is for the exact simulator, whatever the simulator is there, you can directly use that simulator. But the problem is that this is the noiseless circuit, and practically noise is there. So whatever result is there, that is not a correct result in that case. That means you miss something. Missing is the in terms of the noise. Uh, without noise, if my results are very good, but practically when we use the real quantum machines, then the results are not good, because at the time of the simulator you are not consider the noise, you are using this one option in that case. Noise simulator, they consider the noise of every gate and move from one state to another state. They consider the noise and other things. So this is a good option if you want to work in a closer with the practical solutions. So that is the way that how we can use the selection of the simulator. And perimeter shaping and other things are the another way to select the simulator and use the simulator. So all these platforms are given. Once you install this one online, and then you can use, you have the option, you can switch from one to another. All these options are there. This is the architecture of the simulator tool provided by the Google. So here the quantum developers are there. Assume that you are here. Then you write a program and you have the data set, and you put in this one, and their simulator start working in that case. Then simulator transfer or change from one format to the another format, and transfer this information to the Google Cloud service, where the real quantum engine is available. So the quantum engine, they generate the result or share to the quantum computer, simulator, any one of they can select based on the availability or based on your choice. If you select the quantum computer, they can go in this way. If you say that I want to run on the quantum simulator, they go in this way. So put the program, so they automatically change the platform, and after changing the platform, they call the quantum engine. Quantum engine select either based on your choice. You want to work on the simulator tools or you want to work on the real machine. If you want to work on the real machine, your limitation is in terms of the qubits or memories and other things. And of course, the cost is very, very high as compared to this one. If you go to the quantum simulator, there are classical computer connected with the quantum simulator. They solve your problem, generate the result, and transfer to you. So this is the way that how the such type of architectures are working in that case. Yes, the point that the Google, whatever we have discussed so far, the Google, they design a real processor, not on the papers and other things. So, Foxtel, the first one of their quantum processor in place of classical processor is the 22 qubit. But don't think so that this processor directly put on our processor and chipset and working on this. Their demand is very high. That we demand in terms of the requirement for running this processor. That we say, for example, the temperature requirement and other things are quite high. So it is not possible on the that means this current environment, such type of processor can survive or can work effectively. They lost their quantum property very easily. So they designed the 22 qubits quantum processor, and some machines are available. That means I've checked that if you go to the Google platform and see the quantum, some machines are available for your experimental purpose. And then they propose even another chip. Of course, this is also in physical that is available, 72 qubit machine. The qubit processor is there. Then after they start the divide and doing all that type of operations, so they propose the 64 superconductor in a qubit system. So from 70 to 64, but they also support the SQ algorithm. Or by default, they support this type of algorithm suitable for that type of algorithm. So you are not required to write the entire algorithm from the scratch. You can directly use that type of algorithm because they already burn in that case in that machine. So these are the quantum machines, or that means the quantum simulator tools platforms, and these are the hardware chip. So if they have the hardware, of course, that they have the quantum computers. So this is the another way that you can use the quantum computers, not the quantum simulators. So quantum vector machine is there, sorry, quantum virtual machine is there. You can use this emulators tool. They give the same behavior whatever the real machine is there. So all these platforms are there. My suggestion is that please explore this platform and use this. And once we open this black box, that okay, what is going on the quantum machine learning on these platforms? So here, this is the green color is the new one contribution. Blue color is already there. So that means GPU, CPU is already there. QPU or comes quantum processing unit comes into the picture. When QPU comes into the picture, then simulator tools comes into the picture. Then operations point comes into the picture. Then layers and differential comes into the picture. And finally, quantum data comes into the picture. So this parallelly, they add this architecture with the existing one architecture to feel the quantum behavior or to use the quantum operations or the gates on that platforms. So this is the way that how we can aid the quantum machine with the classical machines or work in that case. Of course, all the companies are fighting with each other since 2019. So if Google done the wonderful work, then IBM is why not? So IBM also proposed a one platform that is the known as the Qiskit platform, and this is much more user friendly as per my opinion. And my PhD students are using that Qiskit. So if you are the very beginner and first time you are using, my suggestion is that you need to focus in this platform. And this SDK developed by the IBM, and this is openly free of cost available. You can use these libraries and this platform for simulator program. But when you use the simulator, that give a same phenomena, same behavior, because what's happened that they put all these constraints, whatever the hardware constraints are there, and of course the Qiskit also give a connection from your PC or your system to the real quantum computers. But when they give the connection from this to this, you have the limited credits are there. One thing is that you need to purchase the real quantum computer processing credits. Another is the real quantum computers have the limitation in terms of the qubits and other things. But in the simulator, we can do whatever we want. We want to write a machine learning program for 100 qubits and put the 100 qubits. But here, quantum real machine is the 16 qubit, how you can put the 100 qubits. So that means program you are not able to do, or whatever is there that you can do in that case. And similar that is we have seen that IBM proposed the processes are there, processing in terms of the number of qubits as well as the noise and other things. So hardware verification, noise characteristics, error correctness are there. So this is there. That means of course all these are the different, and they propose one by one with different applications, different availability of these things in that time. So all these are the that means here in that case. So it depends on the availability, it depends on your point where which one you want to use models at your operation purpose. Now, by default, Qiskit support the machine learning libraries, quantum machine learning libraries. You can run the QNN and other things very frequently. That means that's a very wonderful platform. At the beginning, within a week, you can familiar with all these things and start working with them. They are very plug and play sort of solutions. The Qiskit and the machine learning libraries and other things solutions are already there. You can directly start using that libraries and run your machine learning program on that case. So Qiskit right now, of course, this is to 2023 slides, maybe possible they add one more options, but that time they support the machine learning library, they support the nature related requirements such as the biological, physics or chemistry problems. You can solve the financial packages are there, and you can use that one for market, stock market prediction optimization. So these libraries, they support all these things, and optimization problems are there. So numbers of complex optimization problem are still not solvable or takes huge time to solve. But here the quantum libraries are there. You can solve these quantum libraries, and if you have some credits or so, then you can use the quantum real quantum machine to solve these problems with the help of this one. And IBM, the quantum simulators, they support noise. That means they're different simulators. This depends on you what type of simulator you want to use. So, say for example, this is the noise simulator with 32 qubits capacity, and this vector they support the 32 qubit capacity, and noise modeling also support state vector simulator is there. Third one simulator, they support the 100 qubit capacity. That means whatever the simulator that is qubits, you can put the 100 qubit at the same time in that. And this is their hardware picture of the IBM quantum computers. So this is the real chipset of the IBM. It's a wonderful chip that comes in the Eagle of this is the real quantum processor of this one. And the size of this processor we compare with the coin of this one. So think about that how come they reduce the size of this processor. And Eagle support the 127 qubit processor, but of course the size is small, everything is small, but that means environmental demand is very high for this processor. The temperature and other things are quite high. So not possible in right now in our departments and other things. And the cost is of course very high. And these are all other testing phase right now. So this is the IBM Quantum. This is another, that is a 64 qubit processor is there. So all these are the pictorial diagram of this. So starting from 2019, all these they start to 2019 for one small size of 27, and they increase their size again and again. And right now that they try to up to 2 flop operations. Falcon Decision is the machine is there. So this is the journey of IBM of the chipset. They designed like this one and add the operations and again and again. So this picture is say that the Eagle is 127 qubits they support like this one. So this is the comparison between the operations or this chipset between each others in the quantum machine like this one. And now whatever we have discussed that is available in this paper, the quantum computer toolkit from Nut and Bolt. So if you want to go more, you can definitely go. In this paper also cover the tutorials and other things. You need to see this thing. And someone want to do the research, so this is the one direction of the research. Recently we upload on the archive that this is so quantum federated learning. I just move from the fundamental to the research. This is only the one slide of the research. So quantum federated learning, what they will do, so that when you go to the IBM platform, when you go to the Google platform, you find out the multiple machines are there, and you need to decide the perfect machine for perfect operation. So in the federated learning, we also do the same thing, that multiple edge devices are there. You need to select some devices, make the cluster of these devices and put the operation in these devices, put other operation on the other devices and merge these things. So same thing in the quantum computing platform. So say for example, if you are required the 8 qubit machine, but no one 8 qubit machine is available, so you can select the 2 qubits for machines in that case and do the aggregation of all these things. So in that case, the federated learning is an interesting picture in that case, and solve the problems effectively. So this is the quantum federated learning paper that we, that we have uploaded. And we find out an interesting result here, quantum federated learning, if we use the cluster-based quantum federated learning in that. So this is the research direction. If you want to work in the research, that is open in that case. Now, if you are the beginner and if you want to write a first program, how we can write the program? So very first, you need to find out the problem. What problem you want to solve? I want to solve the face recognize problem. So very first, you make a simple circuit of the face recognize, whatever you are doing. Then convert the circuit into the quantum circuits like this one. Then make it executable. Then see the result. And once again comes to the classical computer to see the results. So problem normal from our here and there, then after design a classical computer architecture, then after convert into the quantum, then execute on the quantum machines or quantum simulators, then after see the results. If result is as per your expectations, then generate the result and find them. So this is the life cycle of one developer. If they want to develop, they can do developing like this one. So when you write on the IBM how to write the quantum program, very first program is the hello world. So you want to type the hello word in the quantum computer. So you enter the key, that means the states of the symbols in this qubit machine. So if you write like this one, then of course there are 2 qubit machine. You put your inputs here and you can print the hello word very easily. This is like pictorial diagram or Bell state of this one. So when you go to the simulator tools, you can very easily find out, okay, I enter the first qubit, I enter the second qubit, do the operation, what operation is that is the result. Then after I use the measurement unit, I use the measurement unit. As we already know that whenever you use the measurement unit, you convert from quantum to the classical. You lost the property of the quantum, so either 0 or 1. So if you enter the image, they do some operations, then you can see that whether this is the name of that image is correct or. And this is the library Qiskit IBM library, that how you can write the program. You need to call some libraries, already written libraries. You are not required to design the libraries of this one. Say for example, how we make the quantum circuits, call the libraries. Whatever the registers are there, universal register, all registers are there, then you can import all the registers. Then you want to use the classical registers along with the quantum, you can use this one. And then Qiskit other libraries or folders are there in that case. This is your input, qubits are input, because here we can take the 2 qubits input and the output is the 2 classical bits. Then after do the operations, whatever the gate is, gate 8 is there. Then use the generate the result, see that. So and every all the functions are already written. You need to only the take the inputs, then do the operations, or gate is there, then see the result and do all these things in that case. So if I'm using the that means some comparison between two images or words and other things. So we see that okay, the accuracy is very good and almost equal probability they design this and that one. And this is another example of this quantum that bracket example is there. You can write like this one. So this is another platform for writing the program on the quantum. So all these are the different program, but IBM Qiskit is a wonderful job. That means it's very simple. Here, little bit complexity is there, but of course the result is the same in the both the case. So results are almost same in both images or in both the cases of quantum. So this is all about from my side the quantum. I think so. You all are familiar and find out something. So please, any queries there? Thank you very much from my side. This is all about. Yeah.
Thank you so much, sir.
So
We'll take the queries first. If any.
yes.
Shall I read out the question, sir?
Yeah, please.
Is the number of qubits in machine is same as RAM size in the classical systems?
No. Qubits is same as the bits. If you perform the 2-bit operation, that is the 2-qubit operations. Like this one, bit and qubit are the synonyms indirectly, not the RAM size. So, in place of bit, we can take the qubit, but the property is the state between 0 and 1 is also a state. So, numbers of states are possible within 2 qubit. But even 1 qubit, they have the multiple states are there. 2 qubits are multiple states are there. But in the classical computer, only 2 states are there. So, we need a more binary operations in that case. Here, we are not required the binary operation in that case. Yes.
So
Another question.
What is the difference between quantum annealing and adiabatic quantum computing?
Ending gives that is some sort of entitlement or angles in that case. Quantum computing covers a broad view. That means they covers all the operations and other things in that case. Ending is that is up to the entitlement and other things, angle, whatever that properties is there. That is only up to that one level. But another is that class we talk about entire architecture sort of thing. What gates are you are using? That is also the part of that one.
So any practical applications of quantum superposition and entanglement?
Yes, face recognize is the interesting problem that quantum machine learning they solve the whatever the problems of the quantum computers. Sorry, normal computer, classical computer, deep learning, machine learning problem. But only the constraint is that the process that means qubits limitation is there. So at the simulator you can do whatever you want, but as a hardware point of view, as of now, hardware is not ready for high number of or large number of qubits. So classical computer, we can make a complex architecture of deep learning architecture, but how we can execute this deep learning architecture into the quantum machine, convert and then use because of the limitation of the qubits or the hardware qubits are there. So because of that reason, we are not able to use quantum machines or quantum, but at the simulator point of view, you can do whatever you want. You can do that things. And
in quantum processor systems, we do have RAM slots where data has been stored.
data also stored in the quantum material is the different that don't compare the hardware of let's say for example processor RAM or motherboard in this case. That is the little bit that means their storage is the different, because if you try to store the qubits or that is the state, then you lost your properties. So I don't think so the RAM increase the RAM makes the quantum machine of qubit, you can increase the speed of the quantum machine, because at the same time you can perform the multiple operations simultaneously. And right now the numbers of online platforms are there with this IBM and Qiskit and other thing. They can automatically generate the quantum circuit, so you are not worried about that how to generate that. Say, for example, if you have the classical computer or classical program is there, you can put and they give somehow the quantum circuit or generate the quantum circuit. Only the problem is that whatever they are generating the circuit, that is not the final. Maybe possible sometime you need to twist or you want to use some different type of the gate in that case. That type of exercise is required in that. Finding a more application of quantum federated learning in communication aspect is the difference. See, we are not talking about the quantum communication is the that means either there are two ways are there. Either you solve the problem on the quantum and you can use the quantum communication in that case, so that you are not required to change the property from quantum to classical. Or if your communication is the normal communication, then first solve the problem on the quantum platform, and then you can do one thing, that you can convert quantum to the classical, communicate the data, and once again classical to the quantum, change in that case. So this is the way that how communication is doing. But quantum communication is still is a challenge as compared to quantum computing. Differ from the traditional software compilation, and what are the key quantum computing or quantum circuits are working on the gate, and in your traditional software compilers they are not working on the gate logics and other things. So that is the main difference. If we are roughly, we say that this is our difference in that case. So I think so we have seen all these queries, and if anyone has any other query, definitely they can mail me. And I also suggest that if anyone want to do on the quantum computing or want to work with us, then definitely always welcome here.
Thank
Can
you,
you
sir. Really, it was very wonderful and very insightful presentation, as you have started from the fundamental concepts and walk through to the entire quantum computing. There is so much to learn. We are in the very starting of the quantum computing. So all the aspects from the qubits to gates, circuits, and all the architecture, everything you have been touched. So it is like, for the first section of this FDP, it is very, very interesting and helpful for all the participants. On behalf of all of us, I would like to express my heartfelt gratitude to you for delivering such enriching and thought-provoking session. Thank you once again, sir. And I wanted to, we hope we will have a future sessions also, if possible. Thank you, sir.
Yeah, sure. Thank you. Thank you very much to all the participant and organizer institute and Dr. Silpa for this wonderful FTP,
Thank you.
and of course all the best for the entire program. And I hope so at the end of this program, at least we have 100, 150 quantum peoples in India. That is the really a good thing for us.
Sir,
Thank you.
excuse me,
Thank you
sir.
very
Sir,
much.
excuse me,
Yeah,
sir.
please.
Sir, may I audible, sir? This is Dr. Manjula. Sir, how
Yeah.
the QC will be implemented or utilized in DL, sir? How it can be, sir? So already I am working in deep learning. How I might transfer my deep learning to QC, sir?
So, Anna, so right, first, say for example, you are working on the deep learning architecture. So first you convert your circuit into the quantum circuits in that case. Then after we can think about the quantum machine learning or quantum deep learning. And since either, so you need to decide whether you want to go in the simulator side or the hardware side. So my suggestion is that first take a simple machine learning program. A CNN is the very simple architecture. Take a CNN architecture, a very small two layers and other things, convert that program into the quantum circuit program that we have seen now, that input is there and gates are there, and select 2 3 simple gates, not a complex gate. That is also, I feel that initially if we take the complex gate, then that is the problem. Take a simple gate, simple architecture, put a image classification is a very simple example, see the results on the simulator platform, then go to the classical quantum computer, and then after make some complex deep learning architecture is still a problem on the quantum, because they are working on the gates have the limited processing. That means gates are the AND gate or gate, whatever the gates we have seen, that the reverse gate, R gate, X gate. And say for example, if you directly use the LSTM cell required numbers of gate for one LSTM. It is not possible directly. So use a simple CNN architecture, convert into the quantum circuit, see the result on the simulator, then convert, use the quantum computer, then after add the complexity as a classical computer machine learning program in that way.
Okay, sir. Sir, and one more thing, sir. Sir,
Yeah.
and the quantum computing will be utilized for used for NP hard problems or NP completeness problems, and how it can be used in a DL, sir. This is my basic question, sir. Uh,
See,
because it require that is QC will require a more number of data sets, and deep learning also which requires more number of data sets. And here it required the NP completeness problem or NP complex or hardness problem. How it can be used, sir?
so deep learning and NP hard, NP complete are the different things. You know, deep learning
No,
is a algorithmic
QC
way to
can be
solve the
used in
problem.
quantum
And
computing. Yes, sir.
so NP
Yes,
and
sir.
the deep learning is a way to solve the problem. You know, either that is if you want to design an algorithm, we can say the deep learning algorithm. NP complete, NP hard is the set of the problems. You know, these problems are the NP hard because of they are not solvable. NP complete because of requirement of this one. So like this one. So quantum, that see, we can't say the quantum is a completely different. They are also a mechanism. They are also the algorithm, but because of their speed, they can solve these type of problems. So, say for example,
Okay,
classical computing required 1,000 years, you know, and they are not able to search all the dimension. Still not able to search all the dimension, even they give you the time of the 1,000 years. And quantum, they search in the all the dimension in a faster fashion. So that's where we say that okay, they can solve any complex problem.
yes,
You know,
sir.
so very first slide we take the example that if you have the 100 lanterns or lamps are there, they are not able to compare with the one light bulb is there. You know, so that is
Yes,
that
yes, sir.
the so quantum. Why we say the quantum is solve the problem of NP? Not because of they have the different, but because the searching dimension is all, and also the speed of the searching is very fast in that. And deep learning is the algorithm type.
Yes,
Yes.
sir. Yes. Sir, and one more thing, sir. Sorry, sir.
Yeah.
Sir, computer vision. I'm working in computer vision, sir. Sir, any papers related computer vision with quantum computing? Can you refer, sir?
Yeah, sure. And just drop a mail. I will share the paper. That is one paper comes in 2019 onwards. That is the CNN used for image classification using quantum machine learning. That is very simple of first paper. Then huge citation is there. CNN for image classification using quantum machine learning. So
Oh,
they take a CNN architecture sample, convert into the quantum machine learning. Then after take a image data set and do all these things in that case. So that is a very interesting paper, at least for the beginning point of view, how we can shift or from classical computer or machine learning to the quantum in that platform. Yes.
yes, sir. Yes, sir. May I get
Okay.
your mail ID, sir?
Yeah, mail ID and okay,
Sh-
and
It will be shared, ma'am. I will be sharing.
Ye- Yes, ma'am. Yes, ma'am. Thank you, ma'am. Thank you,
Thank
sir.
okay.
thank
चलिए,
you, sir.
thank you. Yeah, है ना, चलिए, I stop it here. Bye.
Thank you, sir. I request all the participants to fill the feedback form. And within 5 to 10 minutes, we'll start the second session. I'm waiting for the resource person to join. Please don't leave the meeting. It will be start in 5 minutes.